Good afternoon, everyone. Seems we have the room is brighter, right? What's going on? They changed the bulbs. Right. Okay. So let's have a quick recap about what we have learned on Monday. On Monday, we want to know something which is non-ideal gas. So before we want to know the pressure, temperature, and value related to the non-ideal gases, the first thing we need to know is the critical temperature and the critical pressure. And this leads us to understand what's the supercritical fluids. So as you know, this is a phase diagram of the carbon dioxide, right? So as you can see, this area is called supercritical fluids. So the region, the place, the condition, we want to know why the supercritical fluid is that the temperature have to above the critical temperature, and the pressure has to above critical the pressure need to be above critical pressure. In that case, then the situation or the environment we can regard is the supercritical fluid. Okay, so this is what we want to know: supercritical fluid, and also you need to know the definition of the vapor and gas. Right, and then after that we start to introduce you the equations for the non-ideal gases. The first one we introduce is variable equation of state, right? Okay, so this is the table. I want to tell you that I summarized the non-ideal gases, the table. So as you can see, for the ideal gas equation of state, this is the equation you know very well, PV equal to nRT. So there's no parameter, there's no table, okay? But PV equal to nRT can become P over carat become RT. So as you can see, V over carat is volume divided by mole, right? So this is called V over carat. And also, in order to know the density of the gas, so this is the equation Pm equal to dRT. Okay, so you need to know that this is ideal gas equation of state. For the non-ideal gas equation of state, the first one is called variable equation of state. As you can see, this is PV over carat divided by RT equal to 1. So if there is no term B, term C, term D, that will be called ideal gas equation of state, right? But because this is a non-ideal, so you had to modify ideal gas equation of state by these terms. So you have B, C, D, E, F, for example. These are called constant. So parameter. So for B, you understand there are some parameters. Okay, you have B and B0, B1, TR. So what is TR? TR is called reduced temperature, right? This is a dimensionless quantity. TR is equal to what? T divided by TC. Right, okay? So, and then in order to find out the constant, the parameter B0, B1, you need to get the data from the table, which is TC, PC, and omega. Omega is a pizza eccentric factor, right? Remember pizza eccentric factor. That means that because for the polar materials or polar gases, the pizza eccentric factor will be not close to not go to 1, right? Okay. So this is the variable equation of state, and after that we introduce the van der Waals equation of state. The van der Waals equation of state, as you can see, the equation is represented like this. So this B and A and B, they are all constant. So you understand A is equal to this one, B equal to this one. And you also have terms, some terms of TC, PC, right? So what you need to know is find the table related to TC and PC of the gases, for example, carbon dioxide or nitrogen or hydrogen, for example. Right, and then last one, and we give you some examples on Monday, is the SRK equation. So SRK equation, again, is a kind of modification of this van der Waals equation, right? So these two are also called cubic equation of state, because these are related to the cubic of the volume. Okay, cubic of the volume. And as you can see, if this P go to this side, this will be a cubic function. Okay, so again, you have some parameters, and you have you can find TC, PC, and omega from the table. Right, so this is the summary of the 5.3 non-ideal gases. So when you think of the materials or substance in a gas phase, everything you need to think, the things you need to remember is pressure, volume, and temperature, right? So for the PVT for gases, you can get it from the experimental data, or ideal gas equation of state, or variable equation of state, right? This is for non-ideal gas. Non-ideal gas, we already introduced this to you as RK equation of state. Okay, so you have 179, you have some paragraphs, 179. So please read it by yourself. And the equation, I introduced this to you, these are all related to single species. For example, variable equation of state, van der Waals equation of state, SRK equation of state, they are only applied to single species, not for a mixture gas. For multiple components, like a mixture of the nitrogen, carbon dioxide, or hydrogen, this cannot be applied. Okay? So today, let's move to section 5.4, the compressibility factor equation of state. Because as you can see, for these equations, there's some something missing, or something which is not very good. Is that if we have a mixture gas, a mixture of the gases, like three kind of gases get together, you cannot apply this equation. So do we have a better solution for this? Yes. Today, that's why we are going to introduce you the compressibility factor equation of state. Okay? 5.4. So what is compressibility factor? So when you think of this, you understand if this is ideal gas, PV over K ideal divided by RT will be equal to 1, right? This is the case of the ideal gas. So ideal gas equation of state, we say this is equation 1. However, if this is not ideal, so you can use a Z here, Z. Why? Because as you can see, this is variable equation of state, and if this is not 1, you have term B and term C and term D here, right? So that means that this is not an ideal equation of state. So if you put this all together, you might regard this as a one term, which is we use Z to represent. Okay, so PV ideal over K divided by RT equal to Z, which is Z is not equal to 1. If Z equal to 1, this is the ideal gas equation of state, right? Okay, so this is equation 1 and this is equation 2. So when equation 2 divided by equation 1, then what you can get is what? What you can get is Z, right? What you can get is Z. So Z is what? because P is the same, right? RT is the same for the equation 1 and equation 2. So Z will be V ideal over Kara divided by V real over Kara divided by V ideal over Kara. Again, this is dimensionless quantity. So it's a kind of ratio of the real value and ideal volume. That's why this is what we call so Z here we call it compressibility factor. Okay, compressibility factor. So you can write down something like this: P over Kara equal to Z RT. Z here. And the PV equal, or if you want to remove the over Kara here, you can write down PV equal to Z nRT. Or if this is if you divide it by time here, this is volumetric flow rate. Volume become volumetric flow rate, the mole become molar flow rate here. You can V over dot equal to Z N over dot RT. These are also can apply for this compressibility factor. So as you know, how can we determine Z here? So you know that Z will be the function of the temperature, right? Z will be the function of temperature and the pressure. And because Z is a compressibility factor, so regardless of the volume. So Z will be the function of the temperature and pressure, and also different type of the gas, like carbon dioxide, nitrogen, helium. So Z is, if you change these three factors, Z will be changed. Okay? Z will be changed. So let's find out if we have Z can be changed by this. Can we have a table to represent compressibility factor? Yes, we do. So compressibility factor table you can find out in the Paris Chemical Engineer's Handbook. Okay. So for example, Z equal to P over Kara divided by RT, right? So Z is a function of temperature, pressure, and species. So for example, we take out the species here. So Z is a function of temperature and pressure for air, because air is species, right? Argon, carbon dioxide, carbon monoxide, hydrogen, methane, nitrogen, oxygen. So you can say that at least oxygen, the compressibility factor of oxygen can be related to different temperature and pressure. Okay? But however, you have so many gases, so you can have many tables. So we cannot have all the tables for you. So these are limited numbers of other compounds. So I just want to show you one of the example. Let's use air as an example. So the compressibility factors for air at different temperature and pressure. So in this line here is the pressure. Pressure 1 bar, 5 bar, 10 bar, 20 bar. And for this is temperature, 75 Kelvin, 140 Kelvin, 400 Kelvin, something like this. So this is the compressibility factor, okay, for air. So let's take an example. You know, if this is equal to 1, Z equal to 1, what means that? It can very close to ideal gas. So Z can be less than 1, which is 0, in this case. In this case, 0.9539, the pressure will be 200 bar, 20 bar. The temperature will be what? 200 Kelvin. So Z can also be greater than 1, which is, as you can see in this condition, 40 bar and 400 Kelvin. So for air, you can create this kind of table. For carbon dioxide, for nitrogen, you can also create this kind of table. But this is not perfect, right? Because if I ask you what's the compressibility factor of air at 2 bar, 77 Kelvin. So the number needs to be between somewhere around here, right? Okay, but you cannot get exactly the number. You can guess unless you do the measurement and you put a number in this table. But you cannot make everything perfect, right? So the example tubular compressibility factor, I just show you one of the example, which is air, right? Right, so if I ask you, okay, there's a methane, the volume is about 50 cubic meter per hour. The pressure is 40 bar, and the temperature is 300 Kelvin. And I want to ask you, what is the mass flow rate? Can you tell me? Because as you can see, this pressure is very high, right? So it might not be the ideal gas. So you can use variable equational state, or you can use the van der Waals equational state to get an answer. But another thing is that you can use PV equal to Z nRT. You can find out Z, compressibility factor, and then you put Z in the equation. So you have volume, you have pressure, you have temperature. So what you can get is what? More, right? If you got more, and you got, this is methane, the molecular weight, so you can get flow rate, right? Okay, so I don't want to waste your time, so please, if you get a pressure and temperature, for example, this is the compressibility factor table for air, right? You can also find a compressibility factor for methane. Okay, and you get a pressure, you get a temperature, you can find out Z, value of Z here. And put the value of Z into this equation, then you can get this one. Right, you can get this one, N over dot. If you get N over dot, which is molar flow rate, and then you have molecular weight of the methane, so you can get mass flow rate, right? Okay, so this is easy, right? So the 5.4 B is the law of the corresponding states and the compressibility chart. So, you know, in the previous section we talked about table, but you need to create many tables. But when you have many tables, can you make it become a chart, figures? So let's take a look of this. How can we do it? So we have, because Z, we can have massive value of data, because Z is related to pressure, temperature, and species. So each species has different temperature and pressure. At different temperature and pressure, you will get different compressibility factor. Okay, so if you take out species, you can make a table. Okay, so one species, one table, like I just told you. Air, table 1, carbon dioxide, table 2, methane, table 3. Okay, something like this. Again, it's very troublesome. You can have a book to only talk about the table, right? So for example, the nitrogen Z, what's the compressibility factor of the nitrogen when the environment is 100 atm 0 Celsius. Find out in the table, right? So which is 0.9848. And another example, carbon monoxide, which is 0.2020. Okay? So this table, I just tell you that you can get the answer of this table. However, if we have a chart which can represent, we can put the carbon dioxide, we can put the methane, we can put the nitrogen together, we can make a chart. That will be easier, right? You don't need to check out the table. You don't need to find out a book and find out go to the table and find out the number with the volume. Okay? So that's why we are going to introduce you compressibility chart, which is for all the species. It can apply to oxygen, it can apply to nitrogen, it can apply to helium, argon, something like this. Right, so this is a generalized compressibility chart. And this is important, and I'm sure this will be in your final exam paper. So please, I finally got your attention. Everybody raise your hand and then see what's going on. Okay, good, I'm happy. Now you are awake. Good, so compressibility chart is important, so I want you to work with me on this topic. So the basis for estimating Z in this manner is empirical laws of the corresponding state. Anyway, this is empirical law. So empirical law means what? It's not precisely correct. It's roughly correct. Okay? That means what? The answer you can get is somewhere very close to the true answer, but it's not that precise. Okay, it's roughly right. Okay, so every time when you have a table, you have figures or chart, they don't tell you exactly the answer. They tell you roughly the answer, somewhere around the true answer. Okay, and here, remember we introduced you TR, right? Is a reduced temperature. So TR is this one. You understand? So as you can see, these are the solid line here. This is solid line TR. Okay, this is TR, TR, TR from this one to here. Okay, and there's a number here TR. Okay, for example, this is 1.7, 1.4, 1.3. Okay, this is TR here, this line here. And then PR. PR is this one, this place. The x-axis is regarded to the PR. So if I tell you that in this system, what's the temperature and pressure of the nitrogen, for example. So you need to find out the critical temperature of the nitrogen and critical pressure of the nitrogen. So you can get TR and PR. So once you got TR and PR, the next step you need to find out is compressibility factor. So where is compressibility factor? In y-axis. So this observation suggests that a plot of the Z versus TR and PR should be approximately the same for all the substance. So Z is here. So once you have line, the solid line represent TR, the Z x-axis represent PR. So you get a number of TR and PR, then you can refer to a Z here. Z is compressibility factor. We are going to have some example for you, and please work with me. Okay? So this table, this chart is represent all the substance. Again, all substances can be carbon dioxide, nitrogen, helium, argon, for example. So this plot is called generalized compressibility chart. Generalized compressibility chart. Okay, so now I want you to work with me. So this figures is enlarged of this one. Make it bigger. So as you can see here, there is a TR here, right? The PR and the Z here. Okay? So this generalized compressibility factor, ZC is equal to 0.27. What is ZC? ZC is that, well, there's no physical meaning of ZC, but the definition of ZC is PC times VC equal to ZC times nRTC. So once you know TC and PC, and you got a ZC. So this chart is the chart suitable for the ZC, which is close to 0.27. But anyway, at this moment you don't need to worry about this one, because the important thing is you need to know how to get Z from this chart. That's the most important things at this moment. Okay, so what is, if I tell you the pressure and the temperature of the system, and what you need to find out is Z, right? Because you want to get the answer of the volume. So I tell you P and T, and then you need to find out Z. So once you have P, Z, T, you can get the answer of the V over carat. Okay, so in order to find out V over carat, you need to find out Z first. In order to find out Z first, you need to get PR and TR first. So where is TR? TR is here, right? So in order to find out TR, you need to find out TC, right? So this solid line here is represent TR. So this solid line TR here, this line is 15.00. This line is 1.8. This line here 1.8. This line 1.7. This line 1.5. This one 1.4. This line 1.25. Okay, and PR is here. PR is here, and Z is here. So if I ask you, please find out Z from this chart. Okay, if I say that, wow, for example, let me see that. Raise your hand, okay, if you know the answer. For example, if I tell you PR is 3.0 here, right? And TR is 1.5. PR is 3.0, TR is 1.5. What is the answer of Z? Anybody want to tell me? 0.5 point. Raise your hand. If PR is 3.0 and the TR is 1.5, what's the answer of Z? Yes. 0.8,对不对? Thank you. Somewhere around 0.8, right? Because 3.0 is here, right? So you go up here, this is this line, and TR is 1.5, so 1.5 is this line. So you have the point which close to the 3.1, TR and PR is this point, somewhere here. So if you are somewhere here and go up to this place, it's about 0.8, probably 0.81 or 0.82, something like this. So once you know Z, then you know Z, and you know PR and you know P and T, so you know V over carat. So in the gas system, we always play with three things: pressure, temperature, volume. Right? So I give you the pressure and temperature, you need to find out the volume. I give you the temperature and volume, you need to find out pressure. That's what we practice on Monday, using SRK equation of state. Remember? Okay, so this is very good. Thank you. 0.5 point. Okay, so PR, TR, okay, and then Z here. Okay, so how to find Z? How to find Z? Compressibility factor from the chart. As I just told you, there's a gentleman over there who's got the right answer, right? Give a temperature and pressure. I give you, so for example, 300 Kelvin and 1 atm, okay, of the species. And look at the critical temperature and pressure. I tell you 300 Kelvin and 1 atm for nitrogen. Okay, you need to find out the critical temperature of nitrogen and critical pressure of nitrogen. Right? So you have T and TC, you have P and PC, so you can find out TR and PR. So once you find out TR and PR, TR here, PR here. And you can get the answer of Z. Right? Look up the value of the Z on the generalized compressibility chart. So you get Z. Okay, and then once you have PR, TR, you can get the answer of Z. and then using Z here. So from Z, you have P and T, right? P is this one, T is this one, and you got the answer of Z, and R is constant, so you can find out V over carat here. Carat. Okay? Let's practice more, and I'm sure you can. It's not difficult at all if you practice more. Okay? So you obtain V volume here. So there are some more information about generalized compressibility chart. So in the figures 5.41 is a generalized compressibility chart for those fluids having a critical compressibility factor ZC is about 0.27. So generally between 0.25 to 0.29. But anyway, that is the chart for this condition. You can have a chart for other condition. Okay, so ZC is a compressibility chart at critical points. You know this already. So in your textbook, there are some more charts, which is the 5.4-2 to 5.4-4. These three figures are the expansions of the 5.4-1. You just make the 5.4-1 figures larger and zone in to some spatial zone area. Okay? Anyway, I will show you the case later very soon. So obtain Z from PR, TR, right? So you got V over carat. Okay? So and at this moment you might find out, well, professor, something wrong. So if I give you pressure and temperature, you can find out the volume. What happens if I already know volume, I want to know the pressure? Can I get the answer of Z? Yes, this is what we call ideal critical volume. So if I don't provide PT, or I just provide one of these two, and I give you the volume, so can you get the answer? You need to get from volume. Okay, so no P or T given to obtain Z. So what can I do? So now we introduce another term called VR ideal. So VR ideal is introduced to eliminate the need for trial and error calculations in the problems where temperature or pressure is unknown. So this is the place. You know, we just know this is PR, right? This is TR. And actually there's a dashed line here. This is VR ideal. The dashed line here. I'm going to enlarge to showing you. Anyway, please remember this definition. You need to do the calculation if you need to. So VR ideal, what's the definition of VR ideal? VR ideal is what? Again, is V over carat divided by V sub C ideal over carat. Right? So if you say P or T will represent the same thing, right? T is equal to T divided by TC. So VR will be V divided by VC. But there's no VC, right? What you know is you can find out TC and PC. There's no VC. The critical temperature of critical volume. I never told you about critical volume because it never exists. But if this is the ideal, you can use ideal equation of state. Okay, so VC ideal will become, VC will be replaced by TC and PC. So you know how to find TC and PC. Okay? So as you rearrange this equation, you can get something like this. So VR ideal is PC times V over carat divided by R times TC. So under this condition, if I give you volume, and you only know the T, you only know there's no P or T needed. So if I give you the volume and the pressure and temperature, you can get the pressure. Okay, I have some example for you, so please work with me. So this is, remember this line here is PR, and the solid line represent TR, and VR ideal is this dash line here, dash line, VR ideal. So either you can get this line, this one, and this one, you get Z, or when we learn is VR, TR, you got Z, right? And now you can have VR ideal, TR, you can get Z. Or VR ideal and PR, you can get Z. Okay? Anyway, I just told you that VR ideal has no physical significance because, you know, when you introduce VR, you need to apply critical condition. And there's no ideal in a critical condition, right? Okay, so there's no physical significance. There's no meaning of, there's no physical meaning of the VR ideal. Right, so this is the figures 5.4-2, which is represent the low pressure of these figures. This is the big figures, represent all. But if you zoom in, and this is the low pressure region. Low pressure region. So you can see more clearly that, again, the same as that this x-axis is PR here. Okay? And then this is the solid line represent TR. Right? Solid line represent TR, which is 3.00, 1.4, 1.15, and 1.05. Okay, this represent TR. And then the dashed line represent VR ideal. VR ideal dashed line here. Okay? So if I ask you if the TR is 1.4 and the VR ideal is 1.4. So VR ideal is 1.4 and VR ideal 1.4 and TR ideal is 1.4. What's the Z? Value of Z? Anybody want to tell me? 0.5. VR ideal is 1.4 and TR ideal is also 1.4. Could you please tell me what's the answer of Z? Anybody? 0.5 point? If you don't have good midterm exam score, raise your hand. VR ideal is 1.4 and the TR is 1.4. So what's the answer of Z? Yes. 0.90， 好来，0.91，好，我们来看一下啊。TR ideal 1.4, right? 1.4. This is 1.4 solid line, right? Solid line here, and VR ideal is 1.4. 1.4 is here, right? So this is the point. So if you relate this point to here is 0.92. 你刚才讲 0.91, right? 没有关系，还是给你对了嘛，对不对？哦，你已经很棒了，是不是？哦。So can you get? Could you please? You know, I'm a gentleman. OK， 我很希望给你们多一点分数，所以你只要勇敢，对不对？你期中考如果考不太好，哦，这是一个好机会，对不对？哦，专心听就可以了。好 ，OK，Thank you. So if I give you if I tell you VR ideal and TR ideal, you can get Z. If I tell you VR ideal and PR, you can get Z. right? If I tell you PR and TR, you can get Z. So using this equation, using this compressibility chart, you can find out a value. You can get a pressure, volume, and temperature. So this is what we call generalized compressibility chart, 通用型的, right? Okay, the important thing is VR. How do you get VR ideal? Using this equation. I won't tell you this equation in your final exam. So you need to remember this. Actually, this is not difficult at all, right? This is not difficult at all to remember. Okay? Right. So this figures 5.4-2 is for low pressure, and this figures 5.4-3 is for medium pressure. Again, you have TR, which is solid line, VR ideal, which is dashed line, and the PR, right, which is reduced pressure in the x-axis. Okay, and again, this is Z. Okay. Right, and figures 5.4-4 is high pressure. You have, again, PR, VR ideal, and the TR. Okay? So now the procedures of using the generalized compressibility chart for PVT calculation. PVT is very important, right, in gas phase. So what's the procedure? Procedure is that if I ask you carbon dioxide, you need to find out the temperature, critical temperature and the critical pressure of the carbon dioxide, right? And then this is important. If the gas is either hydrogen or helium, these two are very small and light material, light atoms. So you need to do adjustment. So adjust critical constants. This is called Newton's correction. So once you have this, the critical temperature need to plus 8 Kelvin. The critical pressure need to add 8 atm. So this is what we call Newton's correction. Only apply for the smallest two atoms, which is hydrogen and helium only. So this is called Newton's correction. Remember this. Okay? Okay, this is step 2. Step 3 is calculate reduced volume. How do you calculate? Reduce temperature and reduce pressure, right? Or, for example, you have pressure, you have temperature. For example, you have pressure and you got critical pressure, right? And then you calculate reduced pressure. PR equal to P divided by PC. Okay? And how about the temperature? So the PC is here, right? PR is here. Remember? How about T? T is, you find out T critical temperature and reduce temperature. So TR is somewhere around this solid line here. Okay? How about VR ideal? VR ideal is this one, V over K VR ideal. So VR ideal is this one, line here. So you have x-axis for PR, solid line for TR, and dashed line for VR ideal. Okay? So use two of these three. Again, two of these three. And then you find out Z. You go to the chart, you obtain Z. Right? Two of these three, you got Z. Right? You got Z. and then you take Z back to this equation. Because you got a number of Z, right? So for example, you have numbers, volume of the P, volume of the T, you got Z, you can get V over carat. You can get the volume, V over carat. Okay? So this is how you do how to do your final exam. So the procedures of using the generalized compressibility chart for PVT calculation. Next one is using the compressibility chart TR, PR, VR ideal to get a compressibility factor. Remember? So after you get Z, you can get unknown variables from the equation. You can get P, T, or PV or T. So the good thing about this compressibility chart to get the answer is that easy to do calculation. So you don't need to go to you don't need to find these things in the chart, in the table. Okay, and you can have a chart. You can apply for all type of gases. So easy for calculation, and good for the gas mixture calculation. I'm going to tell you this later because just now we are only talk about single type of a single gas, not a mixture of gases. The best thing about this chart is lack of the precision, because just now the gentleman over there says 0.91, but actually the answer is 0.92. But you know, it depends on different people. You might say, well, this is 0.86 or this is 0.85. So lack of precision, but somewhere around there is just it's not wrong answer, right? It's not a wrong answer. It's an approximate answer. And then what I want to remind you is that in that flow chart, in that compressibility chart, the unit we use is Kelvin and ATM. It's not Celsius or Pascal. It's Kelvin and ATM. So you need to convert the units into Kelvin and ATM in order to use that compressibility chart. Okay, and then remember there are two type of gases need to be the Newton correction need to be used, which are the hydrogen gas and helium gas. And we always talk about absolute pressure. It's not gauge pressure. It's absolute pressure. So when the question tell you the gauge pressure, you need to plus 1 in order they become absolute pressure. Okay? Right. So that's the procedures of using generalized compressibility chart for PVT. Okay, so next is the example. I want you to work with me to this example so it's easier for you to understand. But before we go to this example, again, let's refresh ourselves. Example, exercise this. Okay, so the generalized compressibility chart. So let's go to the page. Okay, this is 100 gram moles nitrogen in a 5-liter vessel at the minus 20.6 Celsius. Estimate the pressure in the cylinder. So I give you the mole, I give you the volume, I give you the temperature. I want to ask you the pressure. So if you use the ideal gas equational state, of course, PV equal to nRT, you can get P, pressure, right? But unfortunately, this is not a ideal gas. So you need to use non-ideal gas equation. You can use van der Waals equational state to get the answer. Or you can use generalized compressibility chart to get the answer, which is much faster than do the calculation using equations, right? Okay, so I give you the volume, I give you the temperature. So what you think is that I want to get the pressure. So let's do, so I give you volume, I give you temperature, I want you to find out pressure. So let's follow the procedure. The first one is you need to find out the critical temperature and critical pressure of the nitrogen. So in your final exam, I will give you a table. I won't tell you what is PC, what is TC. I will give a table and you need to find out these two numbers by yourself. Okay, and remember the unit of the temperature will be Kelvin. The unit of the pressure will be ATM in order to apply these numbers in this chart. Okay, so when you know the TC and PC, then you know the TR and the VR, right? Because you need to find out the pressure, so there is no way you get a PR because there is no P, right? You need to find out VR ideal. And I just tell you the equation of VR ideal, right? So this is the VR ideal here. So please work by yourself. TR will be 2.00. VR ideal will be 0.1161. So you know the TR here, right? You go to 2, and the VR ideal is 0.16. Okay, dash line 0.16. So you can get what? You can get Z. You can get Z. Z will be 1.77. So once you get Z, and you use PV equal to Z nRT. So Z will be 1.77, and the V will be this one, right? 5 liter. And then T will be 20.6, or you need to change to Kelvin, right? So R is constant, so you can get P. The answer of P is 733 atm. This is huge pressure. So there's no way to use ideal gas equation of state to get the answer. Right? So in order to get TC, PC, I'm sure you know already. TR, VR, you know already. So now I want you to work with me to find out how to get Z. For example, TR is 200. VR ideal is 0.161. So TR is here, right? 20. 20 is this line, the solid line here, right? Solid line here. And where is VR ideal 0.161? Dash line 0.161, 0.16. You say, Professor, there is no 0.161. Of course, it's very close. It's just regardless. I just tell you that. Just tell you before this, you don't need to get exactly the answer. 0.16 will be close to 0.161 will be close to 0.16. So you just regard it as a dash line here. Dash line here, and what is that? 20, right? 20 is here. So when you get this dash line, and then you get this solid line, you will get a close around somewhere around here. Right, somewhere around here. So actually it's about, let's say, and then you move this, and somewhere around here, right? So this is 1, so this is, there are 5, okay, this is 1.2, 1.4, 1.6, 1.8. So it's something like 1.8. Okay? So the answer is what? Somewhat is the point here, right? So its answer is, the textbook tells us the answer is 1.77. So when you have your final exam, if you got Z is 1.8, you are okay. Okay? But if you tell me Z is 3.0, of course this is not correct. So if you tell me the answer is 1.8, 1.82, 1.7, that's okay. Right? Okay? Okay, good. Just now we are talking about pure component. There's no mixture. It's not a mixture. So what happened to non-ideal gas mixture? if I have 3 type or 4 type of gas and they mix together. So let's recap what we learned for the single components. So there are 3 ways to get the answer, right? The first one is to do the experiment, to measure the pressure, temperature, and the volume. The second one is what? For non-ideal gas is equations. We learn variable equational state, we learn cubic equational state including van der Waals equational state and the SRK equational state, right? And another one which is easier, we use chart, right? Related to pressure, temperature, and volumes. Okay, so this is what we call compressibility factor. Compressibility factor equation of state. Z, right? Z here. This is for single component. How about multi-components? Multi-component is more complicated. And we introduce you, because you are still first year, so we just introduce you the easiest way, which is what we call case rule. The mixture rule is more complicated. You might learn this when you get to the fourth year, second year, third year, or fourth year. But here we want to introduce you case rules. And the good thing about case rule is it's easy because we use generalized compressibility chart. We use the same chart to get the answer of Z. When you have a multi-components, a mixture gas. Okay? So what's case rule? So the different color and different size of the circles represent different molecules, atoms. So you might have species A, species B, species C. So each species has its own critical temperature and critical pressure. We use TCA PCA represent A species. Okay, so for example, in this case, in this system, and there are 3 types of gases. And there are 3 TC and PC. Okay? So you might say, well, Professor, when I learn how to use the compressibility chart, I need to know PC, TC. I also need TR and PR. So how can I calculate the TR and PR using when I have a mixture gas, a gas mixture? That's why we introduce you pseudo properties. Okay, the first one is called pseudo critical temperature and pseudo critical pressure. So what is pseudo? The pseudo is that you mix up all these 3 temperatures, critical temperature together. Excuse me. Okay, and then we introduce you pseudo reduced temperature and pressure. So you need to remember this. We call pseudo critical properties. And then once you got pseudo critical pressure, pseudo reduced pressure, and you can get the compressibility. You go to compressibility chart to get ZM. ZM stands for mixture. Okay, and then case rule. The good thing about case rule is PV equal to ZM nRT. So if you find Z in a single gas system and you find ZM in a mixture gas system, you can get PV relationship between PV and T. Right, so pseudo-critical properties for a gas mixture. Let's say that, let's think of this. So pseudo-critical temperature, how do you define pseudo-critical temperature? Easy, but you need to remember because I want to tell you one more time, this will be in your final exam. And why not just learn now? It's easier, right? So Tc prime will be species A, the critical temperature for the species A times its fraction. Here it's molar fraction. Plus the molar fraction times the critical temperature of the B. Plus the fraction of C times the critical temperature of C, blah, blah, blah. So this is called pseudo-critical temperature. How about pseudo-critical pressure? Exactly the same, using this equation. Okay? So instead of find out, not instead, I mean, before you go to reduced, you need to find out pseudo-critical temperature and pseudo-critical pressure. And then after that is reduced, pseudo-reduced temperature and pressure. So T and P is system temperature and pressure, right? So how to get the answer of pseudo-reduced temperature? So once you have pseudo-critical temperature, the pseudo-reduced temperature will be easy. So TR prime will be equal to T divided by T prime C. Okay? So you already know the temperature. And then pseudo-critical or pseudo-reduced pressure will be PR prime equal to P divided by PC prime. And you know this PC prime is this one. TC prime is this one. So once you get TR prime and PR prime, you go to compressibility chart. So PR, remember PR is here, TR is here. And now you can use the number, you can use PR prime to represent PR, TR prime to represent TR. So you use the same chart to get ZM. Now here is ZM. Okay, so compressibility factor for a gas mixture ZM can be obtained from the compressibility chart. So TR prime here, you say, well, Professor, this is not TR prime, this is TR. But I just told you, for mixture gas, TR prime can be applied to the TR prime, TR in a single gas system. And this one, PR prime is here. Okay? Well, then you must say, well, Professor, how about VR ideal over Kara prime? Easy, right? Because you know PC prime and TC prime, you just apply the same equation. Okay? So the logic, the way you do the calculation for the mixture gas will be exactly the same as the single gas. The difference is it becomes a pseudo condition. Okay? So let me show you, let me give you an example. So for a gas mixture, you have a P times VR Kara equal to ZM. M stands for mixture, right? RT. Right, so case rule is that approximated volume. Again, this is not precise volume, it's an approximated volume. Value, okay, values. Okay, so case rule, normally, because this is special case, an easy way to do a calculation. So there are some restrictions. For example, case rule is used in a non-polar compounds. And also, TC and PC is less than 2 times. For example, this is A species, B species. The ratio of the A species, the ratio of the critical temperature for A species and B species should be less than 2. Okay, but don't worry about this now. Okay, what you need to know is how to do the calculation. Remember, we just told you that case rule and the mixture rule. Mixture rule is more complex but more accurate. But we are not going to introduce you this one anyway. Right, okay, so this is the example. I want you to work with me. Case rules. Okay, this is the question. This is the 75% hydrogen and 25% nitrogen. This is molar basis. Okay, it's contained in the tank at 800 atm at minus 70 Celsius. Estimate the specific volume of the mixture in liter per mole using case rule. So you have pressure, you have temperature. Then what you need to find out is volume. Right? And then, you know, this pressure is very high and the temperature is very low. So this, of course, this is not an ideal gas system. This is a non-ideal gas system. And this is a mixture gas. Okay, and they ask you to use case rule. So how do you use case rule? Case rule. Okay, first one, solution is you have to find out the critical temperature of the nitrogen and critical system, critical temperature and pressure of the nitrogen, and of course also critical temperature and pressure of the hydrogen. Right? Let's find out this. Remember the step 2? Newton's correction. Because hydrogen here, hydrogen and helium, these are the two smallest atoms in the periodical table. So these two need to do Newton's correction. All the units need to add 8 units. All the number need to add 8 units. Temperature, critical temperature need to add 8. Critical pressure need to add ATM. And then you started to do what? Pseudo-critical constants. So you have pseudo-critical temperature and pseudo-critical pressure. And you have ratio, right? This is ratio. So you know the fraction. Right? You know the fraction. This is 3/4, right? This is 1/4. And then once you know the TC prime, PC prime, you know the pseudo-reduced constants, TR prime, PR prime. And once you know the PR prime and TR prime, you know the ZM. Okay? Once you know the ZM, you go back to PV equal to ZM RT. You get the answer. So get ZM obtained from this 5.4-4. Okay? So in your final exam, I will give you these figures. I'll give you this chart. Of course, I'll change these numbers. And you need to tell me the correct answer. Okay? So go home and practice. So for case rule, under such condition here, after you do the calculation, VR prime is equal to 3.26. PR prime is equal to 33.3. So what is ZM? So PR prime is 33.3. 33 is somewhere here, right? 33.3 is somewhere around here. So you have a line here, right? And TR prime is 3.26. TR prime is here, is 3.26. What is so this is solid line 3.00, 3.5. So it's somewhere between these two lines, right? So it's somewhere here. So you got somewhere in this point. So after this point, you move to here, which is 2, 4, 6, 8. Is 1.8, about 1.8, right? 1.8, 1.84, 1.85, or 1.86. So in your final exam, if you tell me somewhere around the number ZM somewhere around here, you got correct. But you don't tell me this, the 2.2 or 1.4. That's not correct. Okay? So once you have this, then you will get the answer. So please give me another 2 minutes. I want to summarize this because this is important. And I want you to know this very well. And go home and practice. So the summary of a 5.4C gas mixture is that a gas mixture, for example, you have 3 species. It's non-ideal. So important thing, you need to find out the critical temperature and critical pressure for 3 species. And after that, you need to find out what? You need to find out the ratio of these 3 species. Okay, YA and YB. And also you need to know, does these 3 species involve hydrogen or helium? Because you need to do the Newton's correction. Okay, and after this, you can get the answer of the pseudo-critical temperature, temperature or pseudo-critical pressure. So once you get pseudo-critical constants, and next is what? You have T, P, TC prong and PC prong, you can get reduced. This is called pseudo-reduced constants. Either three of these two, TR prong, PR prong, or VR, ideal over carat. So according to two of these three, you go to generalized compressibility chart. Two of these three, go to this chart, you find out what? You find out Zm. Okay? So once you have Zm, you go back to PV over carat equal to ZMRT. So once you have PT, you can get V. Once you have VT, you can get T. Or VP, you can get T. Okay? So this is the way you need to get the correct answer. Okay? So please go home and work on this example by yourself. I'm sure you can get a very good score in your final exam.